I believe you can sit a couple seats here.
Yeah. I think that form.
Okay, well, I'm going to get started. Do you want to? I'll introduce our executive director. Everyone, I think, in the room probably knows Steve Woods, but do you want to say something, Steve?
Probably don't, but thanks for showing up. We do these things every once in a while and try to get a hold of people we think will be interested in a particular topic of the day. And it's nice to see so many faces here for this. Way more than showed up to the talk that I gave a couple months ago.
And I'm going to start right away and just introduce our three speakers, but I think they will also be curious as to who's in the room. So I see Friends of Boundary Waters, Isaac Walton League, USGS, former director of the Native American Studies Program, Minnesota Center for Environmental Advocacy, a job seeker. Anybody else that I
Minnesota
know?
Environmental Partnership.
Sierra.
Minnesota
I'm
Environmental
sorry,
Partnership.
Minnesota Environmental Partnership.
National Environmental Caucus.
Okay, great. So some good policy people for you to communicate with. And let me introduce these speakers. I'm going to start with Amy Myrbo. She's going to be starting off the talk and giving the bulk of the talk. I've known Amy since we decided 1995. She took my glacial geology class as an English major. She ended up getting a PhD at the University of Minnesota and being the main person in charge of the core facility that they have for coring lakes. She's cored lakes around the world, most recently Easter Island. She did her work locally for her PhD on carbon isotopes in Minnesota lakes. I don't know who's going to speak next. Crystal, will you speak after her?
Sure.
Crystal and Cara are both new to me faculty at the University of Minnesota. Crystal's in earth sciences. She's a hydrologist, geohydrologist. I'm going to read her background. Where is she? Crystal looks at integrated hydrologic modeling and field observations to tackle problems in water resources, ecological sustainability, and biogeochemical cycling. So she uses computer models, statistical methods, and real-world data to understand the chemical, mineral, and microbial transport processes that affect groundwater quality issues. She worked remotely on Minnesota issues for a long time on the Bemidji oil spill. And she said it was kind of a strange experience to actually come and walk around that area in Bemidji after having looked at it remotely in so many ways. She has been a researcher with USGS in the past. And then Cara Santelli has a really interesting position where she shares in earth science and in the Biotechnology Institute at the U of M. And that's because she looks at microbial activity on mineral formation. And this has to do with the alteration of minerals, the weathering, the fixation of metals. And she focuses especially on environmentally relevant biogeochemical processes, such as occur in mining and in agriculture. So they are going to tag team this talk. Amy's going to lead off. I forgot to mention the most important thing is that Amy did was research lead on a 5-year NSF-funded project called the Manoomin project with the Lac Reservation, where students at all levels of the tribe were working on research projects on wild rice in particular. So. Take it away, Amy.
Can I just ask a global question?
Yes.
Part of the formal state research that's looking at this setting up a new standard, or
Yeah. No, I was one of the principal investigators. So myself, John Pastor, Nate Johnson.
Stand in front of the camera here, and then we'll switch it over to the.
Yeah, I don't get the press that John does. I think that the reason I don't get phone calls from the media is that I am not a bearded, tenured man. But I've been a little bit under the radar. But I'm trying to change that by handing out. What's that? Yeah. I made these buttons a couple months ago. They say John Moyle was right. So please help yourself. I brought enough for hopefully everybody.
Is there a Wi-Fi access we could share here?
We are linking this, but.
I mean, to the
Link to the talk that you want.
no, just Wi-Fi.
Oh, the Wi-Fi.
Oh, like the Wi-Fi password.
Yeah.
Twitter followers, dying.
It should be, Wi-Fi should be non-point, all lowercase, all one word, for the,
Yes.
for the guests, yeah. So if any of you want to access that, it should be your password.
Yeah.
And then Jen, you're gonna handle some legs, right?
Any other questions about me or anything before we get started? And you can feel free to interrupt me at any point here. So I'm doing this a little bit differently than the talks I've done before, because my understanding, one of the things that you as a group and individuals are looking for is maybe a better understanding of some of the difficult, cryptic, biogeochemical stuff and the scope of what the MPCA study has discovered. And that is not, there we go. Okay, yeah, I hope I don't have it set to like every 20 seconds, otherwise you're gonna be overwhelmed. But so, what I'm gonna do, I'm happy to talk about, in as much as I understand or can comment on the policy and some of the rulemaking the MPCA is doing, I would be happy to do that. My personal opinions about the equation versus the standard, the flat standard, things like that. But what I'm gonna do is talk through the results of the 3 papers that are coming out, that are available online, that I think Carrie's forwarded to everybody, by the group of us who were sort of the several people working on data analysis from the field study that I was the principal investigator for the MPCA. And so there are 3 papers. They are coming out in Journal of Geophysical Research, Biogeosciences, which is an American Geophysical Union journal. It's a fairly high impact journal. And the university is doing a press release also about these, because we know that this is a really important issue, economically, culturally, socially for the state and for many, many people, for many stakeholders in this. So we want to try to communicate this as best as possible. And so there are 3 papers, and you have all these papers. I'm happy to talk through. There are these plain language summaries that I think are a nice way to get into them, but I'm also hoping that these overviews of sort of the chemistry and the different parts of the system that I'll go through here will be helpful in elucidating some of the things that might be somewhat cryptic. I hope that's kind of part of what you're looking for. So the field paper, and let's see if one of these is a pointer. Oh, that's not, that's a mute. That's a that. Sorry. Through the skin, Control Shift F5.
Do you need a pointer?
I
think you can reach it.
probably don't. You'll just see how nervous I am if you have that red dot there. In the geology department, we usually have a pool cue or a fishing pole as our pointer. So
This thing's like a lightsaber, so be careful.
Nice.
I think it is on.
Keeps going. Yeah, well, no, I'm probably just touching it. Okay, so there are 3 papers, and my shorthands for what they are the field paper. That's the one that covers these 100 and some lakes in the state, measuring a whole bunch of parameters in the surface water, in the sediment, the pore waters, doing counts of wild rice plants, and some other plants. So that is, that's that paper. The upshot of that paper is that it's sulfide that harms wild rice. There are a couple of other factors also that are environmental factors that affect wild rice, but the one that we can do something about with the standard is the level of sulfide in the pore waters. So that's the upshot of that paper. The equation paper, or the SEM paper, the SEM is the type of model that was used to develop the equation. So that equation or SEM paper, the upshot of that is that we can predict how much sulfide, how much of this poison is going to be in the pore waters. And the mesocosm paper, so this is a paper where we sampled the chemistry of John Pasteur's mesocosms, 30 of them at different treatments on the same day. And so looking at how all of the different chemistry of the water and the sediments is affected by these sulfate additions. And the results of that paper are that sulfate, so not sulfide, I know this is one of the initial thing that's hard to get your head around if you don't have a chemistry background, is sulfate versus sulfide. I'll try to clarify some of that. But that sulfate, what we think is a really harmless ion in the environment, that sulfate can have other important ecosystem effects in addition to the harm that its product, sulfide, can cause to wild rice. So that there are other ecosystem effects. There are other, and this is kind of my favorite paper, because this is the kind of sleeper paper. This is the one that says sulfate can be a big problem, even if you don't consider the harm to wild rice.
And does everyone know what mesocosm is?
So do people know, are you familiar with John Pastor's research at the University of Minnesota Duluth, where he has these stock tanks that he's been growing wild rice experimentally for a number of years. So looking first at at why you see boom bust cycles in wild rice, about 4-year cycles of good rice, poor rice, getting better, good. And so he started that research a while back. The tribes, Grand Portage and Fond du Lac, funded him to look at sulfate a couple years before the state started funding that research. And so I have pictures that I can show you of what the mesocosms are, but those are these experimental stock tanks. So these are the 3 papers. And so this is the only figure you actually need to understand. I'm just kidding. You don't have to. This is the everything bagel figure. So what you're gonna be seeing this a lot. So I decided that this figure was gonna be basically my talk. And we're gonna move around because this figure shows all of the things that are in these papers. It shows all of the effects, it shows all of the causes, and the different regions of the system where the different papers are, the results of the different papers. So the field paper is really just about, so we sampled a zillion different things and determined that sulfide hurts wild rice. The equation paper has to do with the relationship of sulfate and organic matter and iron with sulfide. And then the mesocosm paper is really not about sulfide and iron at all. It's about what happens to this organic matter when you add a bunch of sulfate, and the fact that you can get a bunch of byproducts that can have other ecosystem effects beyond the effects on wild rice.
So
Yeah.
are we gonna talk about mercury methylation?
I am.
Okay.
Yep.
Thank you.
I kind of related question. I just wanted to figure out what that graphic was you had with the mercury. A little amoeba type form there.
Oh, this guy?
What is that?
This is you can't recognize the sulfovibrio?
Embarrassment, Steve.
Yeah, I'm sorry.
So this is a representation of the bacteria that turn sulfate into sulfide.
Okay, so it's not part of the methylation.
It is.
Oh,
It
Okay,
gives
we'll
you
talk
that.
about
It gives you that for free.
Okay.
It methylates mercury as a
As an extra.
side project. Yep. There's lots of super interesting stuff here. I am also not super deeply a chemist, and so if I pull back from certain questions, it is because I have 2 women in this room who are pros. So I'm a little bit more of a shallow knowledge about a lot of things person. Okay, so that's the 3 papers and these different. So I just want to sort of emphasize that the 3 papers talk about different parts of this system, and I think they're all really important. I know that the equation that one about the relationship of sulfate, organic matter, iron to the sulfide, this equation that the MPCA has proposed to regulate sulfate discharge may be the most sort of proximal one that you all are concerned about if you were writing comments on the MPCA's technical support document and rulemaking. But there's a lot of other interesting stuff here that I think could lead to legislation or other things in the future and could bolster the case of some of the comments. So let me walk through this stuff. So the field paper, I think, is the simplest one to understand and explain. And I can't see my notes, so I'll probably forget to say lots of things that I wanted to say. But the field paper is really just about this relationship, that hydrogen sulfide or sulfide, don't worry about it being H2S. You can just think of it as this poison sulfide is toxic to most organisms. And the results of John Pastor's work in these mesocosms, also in hydroponic studies, and then our field survey, all have converged on the same number for the level of sulfide in the pore water, so the water between the particles of sediment, where the wild rice roots are, getting their nutrients, where they're, taking up everything that they need. Wherever I was going with that, the sulfide is the proximal cause of decreases in seed weight, decreases in the ability of the plants, once they've germinated, to reach the water surface. So that isn't in these papers, that's in a John Pastor paper that came out earlier this year that I would be happy to send you if you haven't seen it. But that's the one that says, these are the effects of sulfide on wild rice in an experimental setting. So we know that very well.
You said what number? Second number?
120.
Thank
That's the next slide. So, and that's the recommendation that the NPCA is putting forward as the number of, and that's one of the things that we have to keep clear is there's the sulfate standard in surface waters that's currently 10, right? But this is a completely different chemical and a completely different number, right? This is 10 milligrams per liter of sulfate in the surface water versus 120 micrograms per liter of sulfide in the pore water. But those are the only two numbers that you have to remember. So the idea behind the NPCA equation is that we don't want it ever to get above 120 in the pore water, and so we want to control sulfate discharge that leads to that amount of sulfide. But I'm getting ahead of myself.
Of 120 in the what water?
Pore water, so the water in between the set, in the rooting zone. So it's basically in this, say, top 10 centimeters. This is partly here because this is what we studied in the field survey. We took these short little 10 centimeter cores to characterize the crap out of the top 10 centimeters. But it's the sulfide, so not sulfide in the surface water. Sulfide requires no oxygen. It's not the sulfide in the surface water, it's the sulfide in that pore water where the wild rice roots are. But what they're seeing. Okay, so that's, the field paper is partly a proof that it's not just in these experimental settings in the hydroponics where we're just growing seeds and plants in jars, or in the mesocosms, which are these stock tanks out in the field, which are partially controlled but open to the weather. So these are more controlled. This is a proof that the field paper is proof that that this holds true in the natural world, with all of the other factors, with water temperature and nutrients and everything else that we measure, all of the chemistry of all of these parts of the environment. The key thing is sulfide, and nothing else really matters. Except for water clarity and water temperature, and I can talk about that, that's in the paper, but the point is that sulfide is the culprit that is harming wild rice, and it does that by not directly killing individual plants, but by making the seeds for next year's plant smaller and decreasing the ability of a plant, once it germinates from the seed, to reach the water surface where it can start to photosynthesize. So it's a little bit more of a population effect, and that's why we see wild rice decreasing over years rather than just being sort of poisoned out. And that's partly why this is a difficult problem. Okay, so I think it's really cool that all three of these very different methods of studying this have converged on essentially the same number, right? There's scattering here. There are some reasons why. So this is, sorry, I should tell you, this is from the technical support document that the NPCA released in August, which is, I think, very good. It is, it's based on those papers, really. So this was written largely by Ed Swain, who's my co-author on these three papers as well.
So explain what we're looking at a little bit.
Yeah, so this is,
Numbers mean.
These are ranges of, and I would have to look back, this is not my work, but essentially these are all different results from hydroponics, from the mesocosm, from hydroponics, and from the field survey. These are ranges with midpoints of what could be harmful, right, sort of the error on different ways of calculating from the amount of wild rice and experimental studies what harmful levels of sulfide.
And so the most conservative estimate might be to go back to like 40 or something.
Yep.
But you're picking kind of a midpoint, or they're picking kind of a midpoint.
Yes, but I definitely would encourage you to look at that TSD, the technical support document, to get the full picture of this. I don't feel particularly comfortable talking about how they chose that. But their initial, the first technical support document a year and a half ago, they were at 160. And they've, I believe, primarily on some things that were pointed out by folks at 1854 Treaty Authority, they revisited their calculations and were like, no, actually it should be 120, it should be lower to be more protective. But that's somebody else's work. Okay, so that's probably all I'm going to say about the field paper, because it's relatively simple, but I'd be happy to talk about why we think that water temperature and water depth also affect wild rice growth. But sulfide is the chemical in the environment that damages them. So how does sulfide get there? Where does it come from? So it comes from sulfate in the surface water. So sulfate is the oxidized form. So when there's oxygen in the surface water, so here's the bottom of a lake, there's no oxygen down in the mud because it's all organic, the balloon crap that Minnesota lakes have at the bottom. So oxygen in the surface water, so there's sulfate, oxidized form, and then the sulfate diffuses or is convected, moves into the pore water. So this mud is really 99% water, about 90 to 99% water. So there's a lot of water in here for the chemistry of the lake water to get into. And Crystal will talk more about groundwater and some other things that we didn't have the opportunity to look at in the field today. And this is definitely advancing automatically. And I could probably fix that, but I'll just keep clicking back. So the sulfate gets into the pore water of the sediment, of the mud, and the microbe here reduces it, so chemically reduces it, converts it, we'll say, to sulfide. And this is the poison, right? This is that rotten egg smell that toxic to most multicellular organisms. In order to convert the sulfate to sulfide, it needs organic matter. So that's the mud, that could be debris of wild rice plants, that could be algae, it could be fish poop, whatever. And so the sulfate is one of that sulfate level. Without sulfate in the water, you can't produce sulfide in the sediments. And then the other thing that happens once the sulfide is in the sediment is that if there's iron in that pore water, iron and sulfide love each other very much, and so that's a very favorable reaction, and the sulfur and iron get together to form iron sulfide minerals. That I've represented here is pyrite, so fool's gold, just as a way to kind of keep that in mind. But basically, if that sulfide isn't free floating around being poisoned, if it is stuck together with iron, it is not toxic, right? So the iron in the sediments, in the pore water, is sort of detoxifying that sulfide by binding it up. And so in situations where there's a lot of iron in the sediments, we find very low sulfide. Where there's very little iron, we find a lot of sulfide in the sediments. Okay? And so you can already see the basis for what is known as the equation paper, the SEM paper, that the MPCA has proposed an equation, a site-specific standard for different lakes. Instead of saying 10 milligrams per liter for everybody, saying, okay, we're going to measure how much organic matter is in the sediment, because that matters, how much sulfide we make from a given amount of sulfate. And we're going to measure how much iron is in the sediment, because that affects how much sulfide is there to poison wild rice. And so these processes are the basis of that equation. So if you have more organic matter, so if you say for a given amount of sulfate, you have more organic matter, you get more sulfide. If you have more iron, you get less sulfide free in the sediments. Yeah.
So this is where I want to ask the question of mercury methylation.
Yeah.
So even if you have high iron, let's say, and you're creating sulfide and it turns into pool gold, which is fairly inert, are you still methylating mercury?
Yes.
So you have a poisoning process going on, but it's not going to poison wild rice, it's going to poison fish and people.
Exactly.
Birds,
Yep.
and otters.
Yes.
Whatever.
And it's even worse than that.
But you're gonna talk about that, John.
But I will talk about that.
So,
Yeah, please, this is good, because I'll just ramble on.
So is sulfide particularly difficult to measure? Is that why they're not measuring sulfide directly?
It is tricky, but it's partly that what they need to regulate is this.
What's discharge?
What's discharged.
Yeah, I understand.
I mean, you can measure this, but if you want to prevent it, you have to take a couple steps back to the sulfate discharge.
Before they permit something. Okay.
Yeah.
All right. I'm thinking of all of those plants out there that are already permitted. So
I am too.
can they
I think
measure the sulfide and have those plants? And
they absolutely, but it's the sulfide happens, that whole process happens in the ecosystem, right? Not upstream.
Mm-hmm.
So upstream is just this, and this whole part of it is specific to the lake or river. And if you've ever walked in a river versus a lake, the amount of squishy stuff is very different, right? So this is a big factor in how much sulfide.
Right. I mean, I
This is why
understand all that. I'm
yeah.
just looking at the equation and thinking, okay, you're taking 3 measurements in an equation to get the final one, which is the sulfide level.
Yep.
Why aren't you just measuring the sulfide?
Right, because you don't want it to get there. You don't want it.
I get that with the nuance.
Here's another question.
Yeah.
So if limits are being identified based on surface water sulfate levels in relation to iron and pore water, what do you expect to happen when in situations where we know that there's a substantial amount of groundwater delivery of sulfate to streams?
Right, where there's a bunch of fresh water coming up. And I'm going to defer that to Crystal's area of research, and she will talk about that after I finish. So, yeah, absolutely, absolutely an issue. And it can go the other way too, where the surface water has a lot of sulfate, but the groundwater has low sulfate. And that may be the case in certain sites where things are, where wild rice is growing at very high sulfate concentration.
there must be some other variables in that conversion other than organic matter and iron. Maybe they're not as important, but what are the other variables? Temperature?
There are not.
That's it?
There are not. Nope, the 3 things that affect sulfide are iron, organic matter, and sulfate. And they affect it about equally. Yep, and that's the beautiful thing about this paper and this method is key through every single measurement that we took in there. And what fell out was these 3 things. And from a biogeochemical standpoint, this makes complete sense. Like if we had to predict at the beginning what would affect it, this is what we would have said.
Even temperature?
Yeah, no, the temperature may control how fast it happens, but those microbes are doing their thing all the time. And the sediment doesn't really change temperature all that much over the course of even a year, right? It's down there 4 to 10 degrees centigrade probably. And so Nate Johnson at Duluth has done some research on that temperature dependence of this process, and it's not very big, and certainly over the number of years, that rate doesn't, the temperature would affect, as far as I can Cara could back me up or tell me I'm full of crap, but that will mostly affect, I think, the rate that the microbes are working at, not the final amount.
Or what the PCA ignores when they say, let's say there's a lot more iron in the sediment, and therefore we get a lot more sulfate to be released without harming the wild rice. We'll just generate more mercury, which does not affect wild rice. And it is one of their areas of responsibility, but they have to silo it off and say, we're only looking at wild rice. It's just a wild rice sulfate standard. We don't care for dumping more.
And they do, I wouldn't say that they don't care, but it's not, it can't be in terms of legality, as I understand it, part of this discussion, right? But we have great evidence now that it should be part of some other rule, that sulfate, but there's active research also going on about that, yeah.
So how accurately, like what's the accuracy of this equation predicting sulfide levels in soil?
Yeah, so
where is that value at?
Right, that is another part of the technical support document and the paper, So I would encourage you to look at those. As far as the accuracy, I don't have that off the top of my head. It depends. So some of the concerns would be, where you sample in the lake. Do you sample near the shore where there's maybe less organic matter? Do you sample out in the, so there are some logistical things that the MPCA is going to have to figure out about how this actually works, as well as the money to do all this sampling.
I want to make sure we have time for you and Jim.
Yeah.
So yeah. Maybe save a few questions for later.
Yeah. You had your hand up though.
I have a question about the form of the iron.
Yeah.
If you go in and measure the iron and sulfate in the sulfide, would it be accessible to this equation?
No.
So
so it's the extractable iron.
Okay, so it's some kind of fermentable iron. There are lots of iron hydroxide as well.
Yep, and those would probably be part of that extractable iron because they will dissolve given the right
so they would dissolve in
conditions.
this process.
Yes.
But they release phosphorus.
That's another good question. You've been doing your homework. Well, you've all been doing your homework clearly, but so I'm going to just motor through. This is most of the equation. Oh, right. Okay, so this is the equation. Paper. And lots of interesting things, because that's where the rubber meets the road, right? For the current rulemaking, this is the one that we really have to be concerned about. But now I'm going to tell you about the ugly sleeper part of the story. Yeah.
Could you ask quickly, if you have high sulfide levels,
Yeah.
that the wild rice has been not there,
Yeah.
is there a chance that sulfide level will go down such that?
An amazingly good question. So there's brand new research. I was up at John Pastor's farm this summer, and the highest sulfate treatments, these 300 milligrams per liter sulfate, where the wild rice was extirpated because of the sulfide levels. He just let them go for a couple of years, and now there's rice coming up. So there is a process. I mean, rice is resilient. It benefits in some ways from disturbance from some of these other things. So it can potentially come back if you stop loading the system with sulfate, which is what he did. So
Any ideas what that number would be for the sulfate?
no, 0, something low. But John is looking into, he's doing a ton of research on a lot of the nuances. One of the other things that I want to say super quickly about this that I know is in John's paper is that this may be non-toxic, but if it plates onto the roots, it can keep the plants from taking up nutrients at certain parts of the season. So that is a real concern about this idea that iron detoxifies. It may detoxify in general by reducing above the sulfide, but it can also have effects on the plants. But this is another active piece of research of a grad student there. Okay, so we know what is happening to the sulfur in this equation. So now I'm moving on to this mesocosm paper that I think is the sort of scary surprise of all this research. We know what's happening to the sulfur. What's happening to all of the components of the organic matter? So what is organic matter? It's carbon. That's what the microbes are using to convert to help them convert sulfate to sulfide, but it's also all this other stuff. It's nutrients, it's oxygen, it's hydrogen, it's nitrogen, phosphorus. And so what happens when the sulfate reducers blow apart, decompose this organic matter, is that all of these components get released to the water column. And so in the musicosms, we found that there were higher nutrients, higher dissolved organic carbon, higher alkalinity in the higher treatments. And so even if you don't have wild rice, even, you can see that the sulfide is not even discussed here. Just the fact that you're blowing apart extra organic matter can release all these things that can have significant ecosystem effects. So this is parallel to what you're saying about mercury methylation. Even if the sulfide is detoxified, even if there's no wild rice there, this is still happening. And so this is the danger of releasing sulfate in general to the ecosystem. This is the equations. This is sort of the quantitative way of showing that organic matter plus sulfate equals some carbon stuff, the sulfide, and then these nutrients, nitrogen and phosphorus, that then go out to whatever water body we're concerned about. This won't necessarily happen just in any situation where you're releasing sulfate. You have to have that mud and the microbes and no oxygen and organic matter for it to happen. So, maybe releasing it to Lake Superior wouldn't have this effect, but releasing it to a wetland that then discharged to the boundary waters or somewhere else would, which could potentially load things with nutrients. Dissolved organic carbon is that brown color in lakes, so that can change the transparency of lakes and affect the ecosystem. Alkalinity can change the buffering capacity of those ecosystems.
Which means its ability to respond to acid rain.
Exactly. Or other types of acidification or things like that. And so this was where I was just going to pause and say, this is extra. So ordinarily, organic matter, so dead algae, whatever, sink to the bottom. Enough oxygen is used up to decompose them as far as they can be decomposed, and then they get buried in the sediments, sequestered. The nutrients or whatever get buried in the sediments. But so because the oxygen is used up, and then after that, it's not very efficient to decompose the organic matter. But if you throw a bunch of sulfate in there, the microbes that essentially breathe sulfate, it takes the chemical place of oxygen. And so you can decompose extra organic matter, and so increase this flux of nutrients, dissolved organic carbon, alkalinity to the ecosystem. And not just that, but mercury. So all organic matter, mercury is deposited from the atmosphere. Algae, it becomes part of a lot of organic matter. And so this is very small, so it's not shown in that equation, in that what I just showed, the nutrients, phosphorus, everything. But we did also find that total mercury, so it's not even getting to methylmercury, but total mercury is higher in higher sulfate treatments, which then is a double whammy because there's more mercury for these guys to methylate as well. So I think this is what I think is the big novel finding of all of this, is that sulfate release can increase total mercury to the ecosystem, in addition to methylmercury, because those microbes are methylating.
So say that again. I thought I heard you say that the actual dissolved mercury in the water body was higher, even notwithstanding the increased microbial activity.
Yes, so the microbes that do this sulfate reduction also methylate mercury, and we could be giving them more mercury to work with as well.
Right,
that's released from the organic matter.
Okay, so it is just part of the biological process.
Yeah, because ordinarily that mercury would be sequestered with the organic matter, but we're throwing another terminal electron acceptor in it, a substitute for oxygen, so we can decompose more of it and release that into the environment.
More fuel on the fire, so to speak.
It's lots of fuel on the fire. I mean, these things. This is this is maybe another rule that needs to be made. This is very unrecognized in the world. There's papers in the Netherlands and a few other places that have recognized the major ecosystem effects of sulfate into wetlands, to these muddy environments. This is a big deal for Minnesota.
And this all happens regardless of the iron.
Yes, and regardless of wild rice, regardless of the
Right.
iron. Right, and so this is, I was trying by hiding that to sort of say, and I'll make this available, it's got my notes in it, but I can make this available to you guys as well.
Is the quantity of organic carbon that's being basically converted to available dissolved? Are we talking about a change in sequestration? So if we were to start methylating or start sulfating, sulfate into a lot of our wetlands, are we going to be decreasing the storage, the carbon storage that exists up there?
Carbon cycle question. You still my beating heart. This is what I did for my dissertation. I don't know. I don't think it's that. I don't think it's quite that big, but I haven't done those calculations. But this is something that we talked about a little bit. I just wanted to show you. So I want to say thank you. In French. I'm not going to try the Dakota because if there are Dakota speakers in the room, you will laugh at me. Gracias, so given the stuff in Spanish. And the papers are available. I think Carrie has them if you haven't all gotten them. I wanted to just show a picture so you know what I'm talking about. These are the hydroponic experiments that John Pastor did. So these are wild rice seeds that have germinated and then are growing. And so sulfide is bad for this stage. They germinate fine, but they don't grow quickly enough. And all they've got to go on is the food that's in the seed until they can get into the light. So that's a major problem. This is one of the mesocosms, so these stock tanks with wild rice, heavily controlled, really a cool experiment. And then here are some of our wonderful field techs and all of the wonderful stuff that they did out in the field. So that's a lot of stuff and a whole bunch of maps, and I'll turn it over to Crystal.
So Crystal, beware, it's on auto.
Can we ask any more questions?
Yeah, you want to while
Are they different microbes that do the mercury methylation and do the conversion of the sulfate to the sulfide?
They can be the same. They can be the same, but there are some other microbes that do the methylation too. But this is definitely a question for Dr. Cara Santelli sitting back there, who can correct me on all the wrong things I've said. Oh my God, it's infinity room.
I mean, what we know about the sulfate microbial community is that they're pretty diverse. There's a lot of different microbes to keep track of. But that's one of the things that I do is keep track of who's doing that process. We're still learning more about the different types of microbes that can do that process, mostly through understanding, like doing whole genome assays of not just looking at who's there, but what their potential is. Do they possess genes capable of reducing sulfate? So that's one thing that hopefully Crystal and I will be getting into, working specifically in northern Minnesota and some of these areas. She'll talk mostly about the project, and I can answer questions on the chemistry and biology.
She'll come and save me for your difficult questions. Okay, so don't worry, I've only got a few slides here, and the main reason is, I think we are here to understand what's going on with the standards. And that's one of the questions we had opening was, were we even involved in the, the research behind the standard? And that was Amy here. And I actually arrived on scene, I guess, about 4 years ago. That's when I moved to Minnesota, and was immediately captivated by this very, very interesting, very important question. But that was after most of the research was already concluded. They were still sort of interpreting it. So I guess I'm joining a little bit more as the, let's see, it's the next chapter sort of going on.
Future.
The epilogue, but then, the introduction to the next part. But I think it is related because, I think the things that I started to look at were everything that was related to what their study was showing. And, this idea that, probably we need some sort of standard that's kind of more site specific, right? So bringing in those factors that could be different among these sites. It is the sulfate concentration for sure, it's still there, but it's also these other factors, the iron and organic carbon, that could be different from site to site, right? So I was really interested then, well, so what are all these other factors about a particular site that could be important? And so I do also want to kind of, launch off from Amy's talk where, I think you had the question about, well, so what's sort of the error or the uncertainty, around what that equation predicted, because maybe why are you guys listening to more information about this if that equation solved it? And I think what Amy really stressed was important is statistically, they looked at all these different things, and it was these factors that were the only ones that had these really strong, so consistent correlations of what was actually predicting sulfide. But are there some variabilities to how much sulfide is being predicted? So unfortunately, I don't have those numbers in front of me, but I mean, it doesn't get to the, decimal point 0.00001 prediction right every time. And then there are all those other questions, there are all those other issues that you sort of alluded to. So how much time do we have? Like how fast would that sulfide actually appear? Does it stay as sulfide? So I think there's also an issue about that. Like, oh, so maybe if we were to then take away the sulfate, could the system sort of revert itself? Or where exactly, there is just spatial heterogeneity, right? There's just variability. Different places in the sediment can look a little bit different. So there actually still are details. And the new standard, I think, is finally really getting at the most important ones, these really strong correlations. But it's certainly also revealing that, kind of a complicated system where there are a number of different factors. And so the part that I became interested in talking with Amy and Evan when I first moved here, because I think there was already a question about, well, but what about the groundwater? What about kind of the zooming out a bit? And I guess those are the kinds of issues I think about. And so what sort of struck me in hearing, about what was going on with the MPCA study is that it was very understandably this picture, this box right here, because this is the top 10 centimeters of where you have the wild rice roots. And generally, we'll kind of get into this, but generally the sulfate is coming in through the surface water, either through, close to discharges elsewhere. This is all where the sulfate is getting. And so this is kind of usually the source of the sulfate getting to the sediment, getting to the pore water, where you have to then deal with organic carbon and bacteria, and whether or not the sulfide is kind of getting taken out of the system. So it's very much the focus. But, what else is happening around it? What about the groundwater underneath? And what if that groundwater has a really different concentration of sulfate than the surface water? Because it usually does. So how does that affect things? And can that be part of the story of why different sites might look different? Still understanding that largely across these many, many different sites that we looked at, and in the mesoplasms, it really were, the sulfate in the surface water, organic carbon in that area, and the iron that really is allowing us to have sort of a prediction of the sulfide. Okay, so that was basically the piece that I looked at, and it's actually a tough problem. So kind of what Amy was also alluding to is actually these issues really kind of like at the fringe of like what in science we're understanding. So this is actually a really major area of research generally in hydrology, of looking at this, what we call like a read zone, where it's kind of code for, oh, it's really complicated. We've got things moving from the top, from the bottom, and so we have to give a really fancy name to capture that like confusion. And so, let's see. So I think actually living in Minnesota, we all have a pretty good idea of kind of what I'm getting at here. So you're swimming in a lake, right, or a stream, and sometimes you put your foot down and you just feel a lot of cold water, right? Like we're all familiar with that circumstance. So I think we all kind of like really understand that sometimes that happens, but not all the time either, right? And it can actually be different in different parts in that lake. And so essentially when you're feeling that cold water, that's groundwater, because groundwater, beneath the ground, that's usually sort of the average over the whole year's temperature. So it's kind of cold in Minnesota. So the average temperature is usually colder than the temperature of the lake when you actually want to swim in the lake, right? We only usually want to swim in the lake in summertime. So, so I think everyone already understands that, yeah, sometimes we have groundwater discharging up into our lakes and streams where we might have wild rice, but that's not always the case. And in fact, we've got kind of this complexity of like maybe one side of the lake has more groundwater coming up than other sides. So in this cartoon, this particular cartoon here, I've depicted where we've been really focusing a lot of our study. We kind of are, I think the real strength to the field study is that, nobody can really say like, well, you only looked at one system, right? It really was statistically robust. We looked at a lot of different places, but kind of in trying to understand sort of the nitty-gritty processes, we kind of did have to go to this one site to study the heck out of it, and hopefully the next steps are looking at how much they sort of extrapolate to other sites. But anyway, this is sort of depicting the one particular site where we looked at, that was part of the field study, and at that particular site, you do have the much higher sulfate concentrations in the surface water. Kind of as a side note, I have looked at other systems where it's really a lot of high sulfate concentrations in the groundwater. But anyway, what I think though, this hopefully depicts is that in systems where you tend to have more of the downwelling of your surface water, you really have the potential to get sulfate much farther into the pore water than if, say, we had some sort of circumstance where we had really strong groundwater fluxes coming up that actually could have some ability to sort of buffer the amount of sulfate that gets into the system. So, and that was basically what we found. That was basically what we found for this system. However, the interesting thing, which I didn't really put in this picture right here, is that even in cases where we have upwelling, even near the surface, you can still usually get some diffusion of sulfate in. And as long as you really do have enough organic carbon, then you can get sulfide, but then, then again, that can be buffered by the iron. So really, it is a lot of those factors that are really important, but this could be addressing some of those issues of, well, is the standard always getting the numbers spot on? And this is dynamic, right? So this is changing over time. So this could be affecting things like how much sulfate actually gets in, meaning how sometimes the amount of sulfite can be changing. Okay, so I kind of wanted to keep this story as part of the, well, I think you guys already got enough homework. Did everyone read all 3 papers?
Is there another in one of the papers?
It is not. So actually this is a separate paper, and I actually did not send that out because I was kind of worried that you might feel like you have too much homework, but I am kind of realizing I probably should put something down here. It's in the same journal, that JGR Biogeosciences.
Send it like I'll
I can do that.
That'd be great.
And it's exactly about looking at this system where we had times periods of a lot of upwelling and a lot of downwelling, and how that actually affected very much so how much sulfate was getting into the system. But that iron and organic carbon are still always a major player in this story. Okay, so are we done now? Well, no. Because there's, yeah, sorry.
Said that strong groundwater inflows to streams could buffer against sulfate inputs, but is that presuming that there's low sulfate inputs from groundwater?
It absolutely is. So this was the really interesting thing. So in this study, we really saw that the concentrations of sulfate in the pore water were much lower when we had upwelling groundwater, but actually at this site, on the Iron Range, there's actually a lot of sulfate in both the surface water and groundwater, and actually there's already a little bit more than 10 milligrams per liter of sulfate in the groundwater at this particular site. So it brought up a lower concentration of sulfate, but actually for this particular site, it still brought up quite a bit. So it starts being, so it's exactly as you say, it starts being a balance of, well, this is being mindful of it's going to bring a different concentration, but what exactly that concentration is going to depend on what you're looking. Yeah.
Now, the equation, you're not talking about taking into account groundwater inflows, are they?
No.
Because those are so site specific.
Yeah.
And seasonal.
It's very, very seasonal. It's, I mean, the surface water sulfate is site specific as well, but no, it wasn't taken into consideration. There's a number of reasons, I think, in many of the sites, and please jump in many of the sites, I think the surface water does tend to be the larger source. It tends to have a higher concentration. I would also say maybe even sort of starts to be a policy issue in terms of what's being regulated. surface water policy and regulation versus
Interesting.
groundwater, which is a can of worms that probably are people in this room who don't know about than me. So it's not.
So is the sulfate levels in the groundwater, what's the source of that? How does that compare with other geographic areas?
Yeah, so those are exactly a lot of the questions that I'm interested in, because I don't think we really know. Okay, if we're going to back up, if we're looking at the state, because there were sites across the state, there's different levels of actual sulfate that occur. We certainly are mindful of that in western part of the state. There's a lot of naturally occurring sulfate. We all know, though, a lot of sulfate is released by mining activities. How sulfate is getting out of mining basins or challenge basins, I think it's still a really open question. And I think the obvious ones are sometimes pumped out, and they're pumped out of pits. And that's very obviously a surface source. And I think that's the obvious one, right? And that's often why, and actually at this site here, the headwaters of this site include water that's pumped out of mining pits. So that's why we have extremely high. Okay, but could it also be maybe leaching out in certain places from the pits and from tailings basins into the groundwater? So they usually have these dikes around some of the basins. That certainly is helping to keep some of that high sulfate concentration water contained. But actually, we do know that those were built more for kind of surface containment. So we actually do know.
They were designed to leak. I mean,
they're designed to leak. Yeah, exactly.
But in
they
order
were
for
sort of designed to keep it into surface water, and actually part of it is that.
But in order for the sulfate to make its way through the groundwater to the bottom of your lake, it has to stay in an oxygenated environment, correct? I mean, you can't change oxidation state.
Right, yeah,
So-
that is true. So
Why not though? Why wouldn't it become, you could have sulfide.
Sulfite, you
too.
gotta go back and forth a few times.
I think you could if there wasn't, if there wasn't iron, like if it got reduced to sulfide and there was iron, it might get, trapped, but I think you could have it.
Well,
Yeah,
it could certainly not all,
impact.
it might not all be converted. So you're right that the sulfate concentrations would go down as it's moving, because if it's not oxygenated, it would become reduced and converted. But whether or not it all could be before it gets to this surface water system, I think these are often being released at the types of concentrations where it won't all have been converted by the time we get to that surface water system. And there is actually evidence, some collaborators who we're working with at the DNR, they look at isotopes, and there is evidence that it's kind of doing the switching back and forth. And also kind of near the surface, near the water table, there is oxygen that can diffuse down through the spaces in the sediments. So probably that upper layer is, there probably is oxygen. And another actually piece of this is, if you actually look here, there's actually another river that was right off the chart here. And so maybe it's also maybe it started out as a surface water source, but when you do have these downwelling conditions, you can get high sulfate concentrations coming down. We measured in the groundwater here, we measured much higher sulfate concentrations here than on here. And where's this water headed?
And just give us some idea, you said that specifically the groundwater exceeded the 10 parts per million. What's, where it occurs naturally, otherwise, what might we see with a naturally occurring sulfate level?
I think in this region, definitely below 10.
Yeah.
Yeah, like 1, 2,
Yeah.
so it's a magnitude question.
It's a big change. I mean, and I can show a map. There's a map, it's figure 1 in the field paper.
There's a map that
sulfate.
were up there for you.
Yeah, and so I can go back to those where, if we want to talk a little bit about that.
Right.
That's climate and geology, it's super interesting.
Okay, so to end here and also to give Cara a little bit of an opportunity to jump in here. So this really is an epilogue of the epilogue, because there is a paper out now showing that there is a sensitivity to the fluxes. But what about, and maybe I should have been a little bit more careful about the how much, it's not even just the how much, but how quickly is the sulfate turn into sulfide? How readily does it stay in that sulfide, iron sulfide form, that pyrite form that kind of protects it? Could it actually reverse and actually become a problem again? All these kinds of things, we don't really understand very well, but what we kind of know are the factors are, who was asking the question about what the funny picture was?
That was
So here's our rendition of,
It's different colors.
it's a different, yeah.
It's diverse. But
Right, we're exactly. So this how fast and how it does it, that's characteristic there. Those are the bacteria, the microbes there. And in terms of how stable it might stay in this form, and actually, to just sort of simplify the diagram a bit, the other types of iron minerals that somebody was asking about, how readily can that become accessible? That has to do with a lot of the geochemical details that, even though it feels like we've measured the heck out of things, we haven't actually we've only really started to scratch the surface of. And so that's the next part, to be able to address some of those questions of how quickly and how dynamic in time, like how much could it change, that we're hoping to dig into next. And so that the three of us are involved in that. And, okay, so that's all the complicated science, right? So the one thing that I know is even more complicated than chemistry, biology, hydrology, it's human beings, I think. I don't really get people. And so kind of what I want to end with is really like the epilogue of the epilogue of the epilogue, because we're hopefully moving forward. Amy, Cara, myself, and actually a team of other researchers, including social scientists. We actually want to circle back and kind of look at this question, why are we looking at this again? Wait, why do we care about sulfate? Oh, because of the wild rice. Why do we care about wild rice? Because there's this treaty. Why do we have this treaty? And how do we actually kind of work with those who are driving these questions to understand what's going on? So we actually have this massively interdisciplinary project that we're hoping we will be able to work on. We're still waiting to find out about some funding aspects
Is this your LCCMR proposal?
No, it's not right.
Okay.
Different one.
Because they can influence those as well.
So we should have had this meeting. We'll get
That's what I can
Nobody wanted to touch our LCCMR project.
Oh, I love it too. It's a little more hot for potato. Yeah, so actually at the U, there's this opportunity for funding for interdisciplinary projects that really tightly weave together science, social sciences. So we actually have this project that we're hoping we get to pursue that, this is where, the three of us mostly have been, although Amy has been involved with talking with tribal resource managers and through the NSF project, right? And so we're hoping to now actually tie together all these different pieces, cultural overtones, and cultural aspects of looking at the physical processes as well, together with all that messy policy and law stuff. And I can only try to attempt to answer any questions about where we're going with this, but there's a whole other part of our team that's really pieces. But we think it's important to circle back.
And very much driven by, so the research questions in this proposal are driven by tribal resource managers. So the questions come directly from 1854 Treaty Authority and Fond du Lac Band resource managers and all of the other folks. Cara Diver, who was the Fond du Lac chairwoman and then Obama's special advisor on tribal affairs, is on our team. And so we've got a very substantial Native component, Native part of the team to really drive, because these are the people, tribal resource managers, who have the most experience with managing wild rice and understanding what's happening with the ecosystems over periods much longer than study periods. So
thanks for clarifying that.
So the light blue area, that is the PCA regulatory region?
So the light blue side, this is, I think I made this figure in a fugue state earlier this summer. So this is, I was looking at it last night and I was like, wow, Yeah, that's the everything bagel. So the NPCA jurisdiction is supposedly the state of Minnesota.
Right.
So both of these colors, it's just the state of Minnesota. But the light blue is lower than 10 milligrams per liter of sulfate, and green is higher than 10 milligrams per liter of sulfate in general. And then this is the western boundary of Wild Rice, pretty much. And this is a little bit of a cartoon, but I can show you the real data below that. And then, so this is partly just to show the different overlapping jurisdictions. Jurisdictions and areas of different kinds of coalitions, treaties, different tribal jurisdictions and groups also. Partly that it's complicated and we need to bring as many of the stakeholders to the table as possible as real drivers of the research question.
Is that the historical limit of Wild Rice, western limit?
No, that's the current. We don't know.
That's just the current.
We don't. So one of my dreams, since I'm a core person, is to look at the remains of wild rice in the sediments of places that we don't have scientific evidence where wild rice is now, because the NPCA's rule talks about wild rice waters, but they're defined as 1972 or whatever, and that is something to be very upset about.
But that does make sense geochemically to me from the point of view of superficial sediment.
Absolutely.
Because the sulfate is much higher in the Red River Low than Tornado. So we've kind of drawn a glacial boundary there.
Yeah, no, it totally overlaps. I'll show you my little maps at the end, because it's so beautiful the way that it's geology and climate. And
Yeah.
it's, we've been looking at paleo for pollen stuff for years.
Urban Lake McCarrons?
The, maybe a little far field, but the national deposition program measuring sites showed that sulfate deposition has been dropping since the 80s, I guess. And just wondering how the amounts that are added aerial deposition relate in terms of scale to the amounts added from water, compared to water.
I think in a lot of places that are receiving, human discharge, like whether it's wastewater treatment or mining or whatever, I think that atmospheric deposition, and this is based on not very much knowledge, but it would be small, but it could be large to places that are naturally low sulfate.
Yeah, it's generally, or I don't know if you wanted to. I was going to say generally that, atmospheric deposition, aerial deposition is definitely low compared to these types of photogenic discharges, to the point where it was sort of the common paradigm before in sort of biogeochemical cycling that sulfur doesn't even enter the conversation when you're looking at non-living synthetics. Like sulfur only, we should only ever have to care about sulfur and sulfate in oceans, just because it's usually such a small amount compared to iron and nitrogen in these in these fresh waters. And that's so to give you at least an idea of just like whether or not people even used to think about it. It looks like, maybe in certain sections, but overall, not so much.
But in this case, we're dealing with rocks that used to be oceans.
Yeah, exactly. So like the western part of the state, there are lakes that are saltier than the ocean.
Yeah.
Right. So when we say freshwater, we should really be saying continental waters, right? Lakes and rivers, because freshwater lakes and rivers can be very different chemistries. It can be saltier than the ocean, and sulfate is a huge player, unrecognized, I think, in large part.
You ready to move on, Karen?
Well, I was going to say, we kind of decided to combine forces, so these slides kind of represented what Karen and I are looking at together, but I would definitely encourage if you guys have questions about sort of more of the geochemistry details and anything about the microbiology, Kara's your person.
I mean, I can add a little bit of clarification.
Yeah,
sure.
Please.
Yeah, so I think if we go back a slide or two, one of the things that Crystal was getting at is that, the mechanistic understanding of what is driving sulfate and sulfide levels is really in terms of hydrology, there could be some major impacts, but also just understanding the geochemical cycle of sulfate to sulfide and the influence of iron in organic matter. What's actually controlling everything is, including the rates at which things happen, is driven largely by microbiology. And that's something we don't have a handle on at all right now. And also, it's more complicated than what we have drawn. We've drawn sort of this simplistic model, but the sulfur cycle in general is really, really complicated. And what we're learning, as Crystal pointed out, from studying oceanography, where people study coastal systems, where there's this huge influx of sulfate into these areas, and what they're seeing are things that we never predicted until recently, is that this sulfate to sulfide conversion, there's a lot of other, what we call sulfur intermediates. So it's not just sulfate to sulfide. There's things like elemental sulfur. There's things we call polysulfides, which are extremely difficult to measure. You would not measure these with most techniques. They're very hard to detect. But what we're realizing is that all of these intermediate sulfur species actually have a huge impact on controlling this whole process. But we're really just scratching the surface right now towards understanding. We call it the cryptic sulfur cycle because it really is, it's hard to see what's going on. And it's something that keeps cycling, and might be controlling these measurements, these sulfide concentrations, sulfate concentrations, organic matter concentrations. So one of the things that I'm really interested in is getting at the nitty gritty. So you might think, why do we care? But it really is getting into what's actually controlling these concentrations. So my expertise is really getting at the fine sort of details of measuring all these weird sulfur species, measuring iron sulfide. So iron sulfide comes in a lot of different forms. We just have it characterized as iron sulfide. But there's a lot of different types of iron sulfide, it turns out. So it's not always pyrite. It could be a mineral we call mechanolite or maconite, however you want to pronounce it. But how it behaves in the environment is going to be very, very different. So if it's maconite predominantly, that might interact with the roots differently, or it might also, it's what we call really reactive. So if there's a whiff of oxygen that comes in, say maybe through a rain event, something that causes oxygen, even just briefly, and a tiny amount of oxygen to get pushed in, that is going to reoxidize back to sulfate more rapidly than, say, pyrite or another iron sulfide mineral. So really getting at the nitty-gritty of the mineralogy, the chemistry, and I also have expertise in microbiology and molecular biology to see, who are the microbes that control this process, but they also control that weird sulfur, what we call the cryptic sulfur cycle. So we're trying to sort of tease apart all these different factors that sort of get into this bigger picture. That's kind of what my addition is. And Crystal, fortunately enough, incorporates all these into her models of what's happening with groundwater flow, which I still think is an incredibly impressive thing to do because it's not typically done in hydrologic modeling, incorporating microbial components and everything into this modeling. So that's sort of where Crystal was speaking at.
Thanks for clarifying with the pyrite thing. I definitely didn't mean to imply that it all goes to pyrite because there are all of these intermediate, there are all these other minerals. Pyrite is stable, that won't reoxidize, but all of these other ones could oxidize back to sulfide too, not even all the way back to sulfate. And so even if this stuff is getting attached to iron, that is highly reversible in these other minerals. So yeah.
Is there any approximation of how much goes into the different iron formations?
It's a little bit of a series, right? The more sulfur you put in, the more closer you get to pyrite, I think. But
it's highly dependent on pH and other things. So there's, you have to look at a number of different factors to determine. pH is important. Iron, the concentration of iron-free iron is important. Concentration of sulfur is important. So there's a lot of different factors that go into whether or not one mineral will form versus the other. Some just take longer to form. And some take longer to form, right? Generally speaking, maconite, which is this really what we call poorly crystalline phase of iron sulfide.
Oh, it's squirty.
The swirly phase. It's this black material, but it's not easy to measure. Most techniques will not use, and if you pull this sediment up and you say take it to the lab and you don't keep it anoxic and you measure it with X-ray diffraction, you're not going to see it.
Change
So-
in the car on the way home.
Yeah, so you have to keep, so it's, you know, all the techniques that we use now going forward keep everything anoxic. So when we analyze everything has to stay completely anoxic when we measure it, or you're gonna completely change the chemistry of the system. It
Have you
happens
ever
very
heard of
quickly.
Randy Toner? Because they got some great pore water extraction methods to do it under vacuum.
So we do that. So that Second Creek, this site, yeah, I mean, I'm assuming you would have done the same extraction
Yeah,
methods
with these
for your
rhizome
field study with the
yeah.
rhizome samplers. So yeah, we take cores, we suction out the water, the pore waters to keep it. I mean, that's,
The
Amy
pore
would have
waters-
never been able to measure sulfide,
Right.
without the techniques that she did. But,
And it's the most important. We knew that we had to spend a lot of brain power on figuring out how to measure the dissolved oxygen and dissolved iron, both of which have to be anoxic to measure.
So I was thinking about your question, why don't we just, sulfide, we can't, it can't.
it's actually really difficult to measure sulfide.
And
I think
accurately. It's expensive. Yeah, super expensive.
So from the formula, the regulatory formula, if we're relying on the concentration as iron to indicate how much sulfide we're going to have in the pore water, in a sense, when some of that iron is interacting with that sulfide, it sounds like we're kind of putting it on the shelf, putting it in a reservoir that at a future date might reverse itself. And so, and I've never heard that in the discussion
Both the
before.
iron and the sulfur, absolutely.
Yeah.
Yeah, and so I mean, so the idea that we can take the sulfate out and lock it up in iron and then it's off the table isn't really true.
Right. And there's other things that you have to consider. Methane is something that we're looking into. Methane interacts with sulfates. There are other things in sulfide. So there are other things in that we're gonna start looking at other things that will change sulfur concentrations, whether it's supposed to be sulfate, sulfide, or sulfate.
Given the sun's chemical uncertainty and future work, I mean, where do you land on this rule? Do you have an opinion?
Me,
Yeah.
personally?
Yeah. because you've done
I
most of
was,
it.
when I mean, I think there are clearly problems with it, but when the equation was proposed, I was coming back from somewhere, I had been out of town, and came back and somebody sent me like a heads up that this thing was gonna be released. And I had no idea, I had been sort of out of touch with the research for a few months and didn't know what they were planning. And I saw this sort of press release, this whatever, that it was an equation that they were proposing. And I thought it was so cool. I just think it's such a smart way to deal with the vast variability in chemistry of these systems. I think it has, we don't, it's the implementation that I think is the issue. How do we measure, how do we get the money for it, how protective do we be? Like how far erring on the side of protectiveness? So I think there are basic implementation issues, but in terms of having an equation rather than a flat standard for the state, I think it's a fantastic idea. And it's the way that environmental regulations are heading, to be more site-specific, to be more nuanced, because different systems are more sensitive, right? So for some systems, 10 is way too high a standard, right? It has to be brought way down. And for some, they're just not as sensitive to sulfate. But there are all these other considerations as well.
So given the sensitivity of these measurements to mistakes, allowing oxygen in the system, but not refrigerating the system, it seems like there's enormous danger that, as you say, in implementation, whoever's hired by a company or whoever's providing staff to the MPCA to do sampling, there could be an enormous gap between what measurements actually come back from sampling and what the reality is in the sediment, unless there are really clear protocols that are written and submitted in, from the scientific community as part of the commenting process. And I'm curious to know whether you're aware of any effort to put together comments like that.
I think it would be the same protocols that the NPCA used for our study. This were developed with the NPCA, so the protocols exist, and the chain of custody and the controls and reproducibility, I think, are pretty. This is not the measuring the iron and organic matter and sulfate is not that hard. So I don't think it's a big challenge. You obviously have to trust who you're hiring, but that's with any research project.
Do you know if some of these things that we said
What's
were harder to
that?
measure are like the sulfide, that's not actually part of what goes into the standard. So maybe we're, as Amy said, we were shown a little bit by the fact that some of those things are easier to measure. I will say the iron extractions, that's a little bit operational, right? So probably we should be following the same protocol for measuring.
Absolutely, and that's, absolutely, they have to decide what they're gonna, what each the yeah. But I think, I think that is something that the NPCA, that, there should be comments on, but that the NPCA has a pretty good handle on what they would propose.
Exactly. Another question in the back, and then we should probably.
How comfortable are you with the 120 number for sulfide as being safe-ish in the first place? Because as I recall in that formula, when you put it in there, it's to a power, So the difference between 120 and 60 that you're calling is a difference of 4 times the amount of sulfate you're allowing. Now, are you comfortable? It's something like that. I don't remember the exact equation. So are you comfortable? Because your original equation has how much sulfide you have as sulfate, and and all of those are low power. They're less than 1 power. So when you flip this equation around, how comfortable are you with confidence intervals and so now it's to a power, as before it was less than 1 power. See what I'm trying to say?
Yeah, I do. I'm really not comfortable enough with the math or the generation of the equation to address that at all. But I don't think it's super sensitive to the. I mean, if you measure, if you have a measurement error, if you have a difference of, say, 10% organic carbon versus 12% organic carbon, I don't think it's particularly sensitive.
I think your question is almost about whether or not how important 120.
Right, the sulfide number, because I'm quite sure that got raised to power over 1.
I don't think so.
You're calculating sulfate.
I don't believe this, but
Okay.
One more question?
Yeah, so you've already identified a couple of gaps in the research, talking about, this potential research project that deals more with policy, law, and the social dynamics of the sulfate standard. I'm curious what other major gaps in the research are out there that you've already identified. Yeah.
One for me is, where has wild rice been in the past? And so I alluded to that. We of course have tribal knowledge and knowledge from people saying that there used to be rice here, but that typically doesn't stand up in court, right? It's not believed. And so what we kind of have to do, instead of, we can support somebody saying, my granny used to rice here, by looking into the lake sediments and seeing if we can find remains of wild rice. So there's these tiny grains of glass, essentially called phytoliths, that are diagnostic of different plants. We can look for those in the sediments. We're also piloted, so we're doing that with tribes now, not with the NPCA. The other possibility, instead of looking for phytoliths, is to look for wild rice DNA in the sediments. So this is not anything to do with the genome or anything, but looking for indicators that wild rice has been there in the past. And we're piloting that, and that works really well. So if there's an interest in getting at something more than the historical, scientific historical record of where wild rice has been and whether it's been extirpated, before it was recorded, we can do that. And I would love to work on that. That's, you know, not, that's related, but maybe not.
More gaps?
Right.
Well, I would say actually part of the aim of bringing in the tribal resource managers and tribes is actually to help us identify some of those gaps, because I would say that until now, I've been pretty fixated with my like narrow expertise from, well, of course I think about the water and I think about sulfur geochemical reactions, but there's probably other stuff that affects how wild rice grows, and those who have been living with it and observing it for years can help us identify some of those. And we've been talking about, so already put together a whole sort of project, water level, so water clarity, a number of these other things, even
Competing vegetation, there's a lot of
competing interactions, ecosystem
invasive and
interactions,
natural.
nutrients, whether or not, how these get metered out like over a growing season, and like between years, all these kinds of things are, in my mind, all potential gaps right now, and that's a lot of
Any last words, Karen?
I think this mercury issue is really important. I'm wondering if anyone is kind of looking at an equation for mercury or something to be able to predict the impact of sulfate levels if we're going to be out measuring sediments or POC and iron and all this stuff, can we now characterize what a sulfate concentration would do to the mercury concentration and a methyl mercury? Is anybody working on that?
Yeah, I mean, that was my current stuff, and I don't know who's, if that's Megan mostly now, or.
Mike Burke was at the DNR Lands and Minerals, and he retired.
Just retired.
Megan Kelly. He retired within the last year.
Burnt?
He RNDT, but his group is in Lands and Minerals.
And I think they've published and written a fair number of reports on it.
Very strong research group within the DNR.
Any university or more independent research being done?
Well, he was university for many, many years. I mean, they run their own little research center within the DNR. They ignore the rest of the DNR for the most part.
So,
And native, and soil, water, climate here.
Review.
Is Randy Toner working on that here?
She works with Ed.
Okay.
And then Nate Johnson, who is involved with the.
And I think Dan, isn't Dan Jones, aren't they working on some mercury stuff too?
Could be.
Is Nathan to you or who's he with?
Yeah,
UMD.
Yeah. And Dan Engstrom has worked on mercury in the past.
And then Swain,
Yeah.
both big mercury guys. So there's a huge amount of interest in that. It's not reflected in, certainly in my work, just because we were sort of, as you said, we were siloed off from measuring mercury at all.
But it would
part
be,
of that because of where the money came from.
it would be possible for you to ask that question among these mercury researchers, suggest a research direction. I think that would be, they would be open to that.
What about the PCA's responsibility to monitor and figure out the source of the sulfate levels in the groundwater that seems to be at least regionally polluted? Or what about, I guess you were asking, the question was about gaps. I mean, that seems like a big gap.
That's a gap, yeah.
Yeah, right. So I guess that is one.
And I guess the PCA has that.
So it's interesting, I guess it's jointly, my understanding, there's also makes me might understand better. I guess it's jointly between the MPCA and the DNR, the DNR. I guess it's.
They
permit the mining, so.
No, PCA has groundwater authority. So.
Yeah.
But it's one of those like boundaries, and so I've worked with both. I've worked with people from, well, actually, probably most directly is with my firm in Pittsburgh. And he is looking, or I guess now more Megan Kelly, who we work with as well.
She worked for the DNR? Yes,
Yeah.
but she was a postdoc, and she was a PhD student at the University of Minnesota, postdoc in their Edwards lab.
Okay.
Very strong.
So she's involved at both of our.
Yeah.
Well, the else is more my big.
What'd you say, Megan Kelly?
Megan Kelly.
Yeah.
Not the famous.
Not the
Yeah,
Megan Kelly. Yeah, so she's been
great.
looking at isotopes to try to get at, where possibly has the sulfate come from, and what has been happening to it along these pathways. Yeah, so I do think, I guess that was really not the intention of helping. You know, even if we change like our discharge permitting, does that really fix the problem if it's mostly leaking out, or if there's still some substantial amount leaking out? And how
Well, the
far is
PCA
that?
is definitely, you know, looking at this. I mean, the MinTAC, the whole MinTAC situation is all about groundwater.
So I think that was, you know, was ACNR, so I was involved in some studies.
Yeah, I mean, not as far as the studies, but I mean, they're looking at that whole.
So I want to give people a chance to lead, but, and I would say that in private, these people might be willing to say, do they trust in the agencies? If you can, who the good scientists are, I mean, there are some solid people working on these projects in the state agencies that we have a lot of respect for, so. Thank you all for coming, I hope you learned a lot.
Well, thank you, it was fantastic.
Yeah, thank you so much for the opportunity to talk to you all. And please feel free to contact me about.
Do we have your contact information?
Nobody ever contacts me, so.
Okay.
Oh, I was just gonna get back to that.
Yeah.